So, solid. Single responsibility, open-closed principle, Liskov substitution principle, interface segregation, and dependency inversion principle. So these are some of the, at least of the more famous principles in object-oriented design, and you can kind of like take many of them also to other types of methods to design and program actually. Single responsibility, for example, could very well be applied in a more functional programming language or procedural programming language. And for example, the clean coding principle is the clean coding methodology, I should say, is quite inspired at least by single responsibility principle. So, single responsibility. There should only be one reason for a class to change. So, this is something that we can for example, find supported by the information expert pattern. And we have been kind of like trying to fix our design in the blackjack game so that this is something that we have been thinking about at least. We have the cohesion pattern also that says that, well, you should have the attributes of a class should be used in every operation of the class, almost at least. So when we change something, there should only be one reason for a class to change. So we should not have these unrelated changes spreading out all over our application. For example, if I would like to change the user interface, I should not need to change stuff in the model. So that's the basic principle in our model view separation principle. So user interfaces change a lot. You should put this responsibility inside some user interface package, and when the user interface changes, I should change that and not the business rules. This is not always that easy to spot if a class has more than one responsibility, but we can kind of measure it. And this is lack of cohesion of methods. And basically, we would like to take the ratio of combinations of operations and attributes and the maximum number of combinations. Higher is better. So the formula is like this. Here I have it. 1 minus the combination of operations and attributes that actually exist minus the maximum number of combinations that can exist. So in the best of worlds, this will be 1, and you will get an LCOM of 0. So if we have the combination of operation and attributes sum up to the maximum number of combinations that we can have, we will get 0 for the LCOM. So O is the number of operations, A is the number of attributes, and this is just a multiplication. And sum OA is the sum of all operations using a particular attribute over all attributes. So we take every attribute, just count every method where it's used, and we do this for every attribute in the class, and we get the sum. So, an example. So we have our circle class here. If you remember back, we have our radius and our nice mathematical circle class. So in the constructor we use it, in the get area we use it, in the get circumference we use it, and in the get radius we use the radius, of course. So the sum here would be the number of operations is 1, 2, 3, 4. The sum OA would be 1, 2, 3, 4. And 1 times 4 is 4, so we would have the lack of cohesion of operations to be of methods to be 0. So, and this is good. The radius operation attribute is used in every operation in this class. Note my pedagogical use of background color. So then we have the a little bit more bloated circle class. If you remember, we added some attributes to handle rendering and stuff like this. And in this example, I just added the position. So in the constructor, we add the radius and the position. And we have this draw function that uses the position and the radius. And then we have the usual mathematical functions that do not use the position. So in this case, we will have 5 operations, 2 attributes. The radius is used in all 5, but the position is only used in 2. It's only used in the constructor and in the draw, not in these 3. So the sum is 7. And then we have 7 divided by 10, and we get 0.3 for the lack of cohesion of methods metric. And this is worse, of course, than 0. So using metrics, you can get measurements on your code, and you can see, for example, if you compare these two ways to do things, this should show you that this last design here is not as good as the first one regarding single responsibility principle. And more exactly, it's less cohesive. This is something that can, of course, be hard to do in a pre-design implementation situation, because you kind of like need the implementation to make the metric calculations. So you have already done your design, but it can at least guide you into refactoring. All right, next principle. Open-closed principle. Maybe this is something that you have heard, that a class or system or subsystem should be open for extension, but closed to modification. So we should not need to change our existing classes when we would like to add some functionality. That is at least the goal. So we would like to change behavior of our application without changing the code. For example, the dealer can have different behaviors, rules, without changing the code in the dealer. And this was one of our goals of using the strategy pattern. We would like to be able to plug in different kinds of rules for starting the game, for handling the who won the game, for handling how the dealer should take cards when it was the dealer's turn to do so. So we would like to be able to change the behavior of the dealer without changing the code in the dealer. Because changing tested and or deployed code is always a risk. If we make some changes in the dealer class, we need to retest it. And this can, of course, be problematic if running test cases manually takes a lot of time and effort. Automatic test cases can also take a lot of time and effort in larger systems. So trying to minimize the impact of changes in existing code is always a good thing. However, it is quite impossible to do this for everything. So you often need to kind of like pick the spots in your application where you think there will be a lot of change, or you need to somehow find out that, okay, these parts have actually changed over the last sprints in our project. So we probably need to make some refactoring or something like that to handle these changes without doing extreme modifications. And we have the protected variations in GRASP and the indirection patterns in GRASP also to make this a little bit more specific. But the idea is that you should be able to extend stuff, change the behavior without changing the code. The next principle, Liskov substitution principle, it's about subclasses. And it says that subclasses must conform to the behavior clients expect from base classes. So we need to, when we do a subclass, we need to make sure that it does not violate the behavior of that the clients expect. And this can be sometimes quite tricky, actually, because as humans we are used to thinking in these kind of like generalization and specialization hierarchies quite easily, but in reality it's not that clear-cut. And if you remember, we have the polymorphism, the 100% rule, and the is-a rule for testing this stuff. And they all tie into the Liskov substitution principle. So I think we have a small example here. So imagine we have this rectangle class. It has a width and a height, and it has a get area function. It also has getters and setters for the width and height. Then we come up with a square type. We need a square in our application. And the rectangle seems like a suitable choice to have as a parent for the square. After all, the square is just a special type of rectangle, right? Seems to work out. And we have the added or modified functionality that when we set the width, well, we make sure that the height is also set to the same thing so that the square is still a square. However, we can now imagine this small test case to test the rectangle. So when we test the rectangle, we set the width and we set the height. I think it should say set height here. So we then add the assert that, well, the rectangle area should be 20 in this case, because I set the width to 4 and set the height to 5. Seems to be a solid test case. However, if we plug in a square here, the area will actually be 25, because we have called this function first, or last. And it will also set the height in the square class. So this test case will break. So we have some unexpected behavior that in the square class, when we set the width, we also set the height. And this is not something that the clients expect. And if we go back, actually we kind of like violated the 100% rule here a little bit, because the square does not really use 100% of the rectangle class. It uses only one of the values, the width or the height, and setting width and height on a square is kind of wonky. It does not really map out really well. Possibly a square has a side instead, a side length or something like that. So this inheritance did not abide by the Liskov substitution principle. We could not substitute the square and the rect for all clients that we could come up with. For example, this simple test case. And we all kind of like need to take care when we do these generalization and specialization hierarchies. And if you think back, we actually did not use them that much when we designed our blackjack game. Rather, we used it as a way to minimize code duplication. If you remember, we had the dealer and the player separated from the onset, and we found that, okay, we have the same types of attributes and some of the same functionality, and then we could use inheritance. So, but you need to take care when you do when you use the inheritance stuff, especially if you do it in a pre-designed situation, because then it's quite easy to run into problems with like this. So if you devise intricate inheritance hierarchies before you have actually coded anything, you are taking a little bit of a risk. I think we can manage possibly to talk about this also before the break. Interface segregation principle. Clients should not be forced to depend on interfaces they do not use. Avoid fat interfaces. So we have touched upon this in some of the lectures in the blackjack game. I've been talking a little bit about that. Well, it's not good for if we expose too much to the controller, for example. Oh, we send in both the dealer and the player objects into the play game operation, and the dealer can actually do a lot more than needed with these objects. So we are exposing the controller to a larger interface than it actually needs. And then we did the facade to minimize this interface to something that was actually needed for the controller. And we could see that, well, it actually makes it easier for the person that implements the controller to actually make the right decisions. It does not have multiple ways to do stuff. But there is also other reasons to do this, to have as narrow interfaces as possible and avoid these fat interfaces that can do anything. So if you have some clients that want different stuff from an interface, different types of clients would like different types of functionality in the interface. So if you have this fat interface, a client wants something new and you add it to the interface, and now suddenly all the clients needs to be updated. So, and this of course is changes in one part of the program should not force changes upon other unrelated parts. And also this has something to do with interface pollution, that subclass responsibilities has a tendency to rise upwards in the interface, and you sometimes have more or less void implementations in 80% of your subclasses. And it's only kind of like one class that really implements the functionality. So this is something to watch out for also. And the example is something like this. We can imagine a automatic teller machine, that is, you go and you can withdraw money from it, and you can transfer money between your different accounts, and you can also put some money into the machine and it will be deposited to your account. And we can see that we have a controller to manage this, and we have 3 subcontrollers, one controller to handle transfers, one to handle withdrawals, and one to handle deposits. And they all depend on a large user interface, a big interface here, with the operations for the deposit, the operations for the transactions, and the operations for the withdrawal. And then we have some implementations of the user interface. For example, we can have a speech system so that it can, for blind people, can hear what the teller is what's happening, and we can have a usual screen user interface, and we can also have a braille user interface, for example, for blind people also. So when any of these, for example, if we make some modifications in the transaction user interface, we would need to update the user interface, and suddenly this would need to be implemented in the braille and in the screen and in the speech. But also, when this interface updates, the withdrawal transaction type is dependent on this interface. So potentially this also needs to be recompiled, retested, and so on and so forth. Because something has changed in the interface that the withdrawal transaction is dependent upon, but actually it's only this transfer controller that needs these changes. So changes spread because of this fat interface that many clients depend upon. So the better way to do it is then, of course, to have a separate interface for all of these controllers, so that the transfer interface has an interface for the transfer user interface, and withdrawal has a separate interface for withdrawal functionality, and deposit for deposit functionality. And of course, the concrete subtypes need to implement these interfaces, but if the transaction controller needs some change, it will be localized to this part. It will not spread to the withdrawal and the deposit types also. And this is what we would like to achieve. Because if we make a change in transfer transaction, we should not need to change deposit transaction controller suddenly, if they are totally unrelated. And we can do this by making sure that we do not add fat interfaces to our clients. And this is something that actually is quite easy to do, and it creeps up on you. Because when you code, it's much easier to just add an operation to an existing interface than to start adding a new interface. So slowly but surely, it kind of like creeps into your interfaces because of your convenience when programming. And this is something to look out for. All right, I think it's time to take a break. So, any questions so far? Good. I will try to get hold of the new links for the extra information during the break. Moving on. Dependency inversion. The principle of dependency inversion says that high-level modules should not depend upon low-level modules. Both should depend on some kind of abstraction. And abstractions should not depend upon details. Details should depend upon abstractions. This will increase reuse and changeability. Typical example is protected variations pattern. So, maybe we have No, this is the last slide. Yes, it is. We will take a look at it in this PDF first. Yeah. So this is the procedural way to do things. You have some high-level procedure function that calls some other functions that in turn calls some other functions and some other functions and some other functions. So you get kind of like a direct dependency from the more abstract to a more specific, to a more specific, to a more specific, to a more specific. So for example, then if you change some detail in the file format, and this is way down in this call hierarchy, everything needs to recompile. Exactly almost as in the way we did with the FAT interface. We changed some part, some client needed some new functionality or change functionality in our FAT interface. We change it, and then we needed to change a whole lot of other clients also, even though they are not actually directly affected by these changes. So this is not something that we would like, because, well, recompiling everything because we did some minute change, but this change was really, really far down and had some kind of cascading effect. This can have, well, effects that we would not like. So the idea then is to put some kind of abstraction in between so that the high-level layer depends upon this abstraction, and the lower-level layer also depends upon this abstraction. So instead of the flow going steadily more and more towards the detailed parts of the system, you kind of like break this flow by inversing the dependencies. So the middle layer in this example has inversed its dependency to go upwards instead of always just flowing downwards. And this will let us kind of like, if we make a change in here, the change stops here, because this layer is just dependent upon the abstraction, not upon the actual details in this layer. So that is the dependency inversion principle. And the example that I have is somewhat similar. We can imagine that we have a client, and we have a button, and we have a lamp. So the client is dependent upon the button, that in turn is dependent upon the lamp. And this means that the client, we have this flow of dependencies from the abstract, the more generic, to the more special. And the idea is then to instead make an abstraction here and let the client depend on the abstraction, and the button implement this abstraction. And the same thing actually for the lamp. So we can break this flow from the more abstract, the more generic, to the more special. And in this case, we also kind of like can see that, okay, we have this on and off actuator functionality in an interface. Instead, we can implement this in not just the lamp. We can have an engine that can be turned on and off, and we can plug this into the sensor quite easily. And a button is just one type of sensor. We could have a sensor to measure temperature or whatnot. So we should strive to invert our dependencies. If we have the case that we have a high-level module class or whatnot, that depends on low-level modules. So try to find an abstraction between these and depend upon the abstraction instead. All right, I think that's it for the solid principles. So we have this single responsibility, open-closed principle, Liskov substitution principle, interface segregation, and dependency inversion principle.